Welcome to the pre-recording of lecture 27 of MCS 481 on computational geometry. So today we're going to see an algorithm, an incremental algorithm to construct Delaunay triangulations. Delaunay triangulations are very important, so I will start by indicating three different software packages and environments, all within Python. We have covered Voronoi diagrams, and there is a link, a natural link between Voronoi diagrams and Delaunay triangulation. So there is this duality, which I will first illustrate with scipy. So in a way, this lecture is in some sense very important as far as uh, computational geometry goes. We are covering many concepts that we have covered already in this course. With software, the lecture can be seen as still more or less self-contained. So if we look at, for example, scipy, um, I introduced the computation of Voronoi diagrams and then also Delaunay triangulations, each time with 7 lines of code. Now it's a little bit longer, but you can see the code to illustrate both the Voronoi and both the Delaunay triangulations is actually very short. So I do not think it can go much shorter. So what is done here in this code is the generation of 10 random points in the plane. The Voronoi diagram and the Delaunay triangulation are constructed and plotted in the same window. Oops, I actually did not have a slide with the plot, but here it is then. So let me execute this Jupyter notebook. So I have 10 random points. Here is the Voronoi diagram. So the points become sites, and the Voronoi diagram is a collection of Voronoi cells. Each cell contains the points that are closest to the site. Remember the post office problem? Go to your nearest post office. So the points are the post offices, the locations of where you can find your post office. And every Voronoi cell contains all, so the Voronoi diagram partitions the plane into regions, into cells, which all have their post office as closest location. So this is the Voronoi diagram. Delaunay triangulations, we introduced them as triangulations where the vertex set, so the points that appear as vertices in the triangulation, are the original given points, and the of all possible triangulations that you could make, the Delaunay triangulations optimize the smallest angle. So in some sense, even though this is a generic and a random configuration, we had some very tiny angles here. All right, what do these two have now in common? Well, this is the plot that shows the Delaunay triangulation and the Voronoi diagram, and I should have had this on a slide. So you can see that you can see the triangles, and so the points from the sides are the vertices in the triangulation. We draw an edge, so the edges are drawn in red. Here we draw an edge if between two adjacent Voronoi cells. Now this construction is rather ad hoc and perhaps it comes out of the air. We will prove in this lecture that the dual graph of a Voronoi diagram is planar and is actually an angle optimum triangulation, and thus it corresponds to a Delaunay triangulation. A Delaunay triangulation because only for generic points is the Delaunay triangulation unique. Okay, so we are using CGAL in this course, the computational geometry algorithms library, which is very useful, very extensive, but very useful when considered in Python. What is relevant, so I will go back to the Jupyter notebook, what is relevant for this lecture here is that in CGAL, the construction of the Delaunay triangulations works incrementally. So we will introduce an incremental algorithm, and in the next lecture we will analyze this incremental algorithm. So the first exercise continues the Jupyter notebook where we illustrated the duality between the Voronoi diagram and the Delaunay triangulation using an example computed with scipy, with a spatial module of scipy, but the exercise asks to do this with the CGAL code. So how do we use CGAL? It's a little bit more complicated, but not that more complicated. So I continue here with the set of points. So we use the coordinates that were generated by NumPy. We convert them into the point underscore 2 object. And then we define a Delaunay object. So a Delaunay triangulation underscore 2. And we insert the points one after the time. Not a surprise here, we did not lose any points. So the vertex set of the Delaunay triangulation equals the set of points. So we have 10 points to begin with, 10 vertices. So we can print them one after the other, and you see that actually the order has been respected. Same order of insertion. Here we also have, we don't have 10 faces, we have 12 faces. In the previous lecture, we had exact counts for the number of edges and the number of faces. So it could be a very good exercise also to verify these counts with the code here. All right, so we can print all the triangles. So it lists the coordinates of the triangles, and we can also print the edges. Some of the edges will be infinite. And you can also count the edges here. Again, then verifying the theorem that we have seen in the previous lecture. But it's very important for the complexity of a Delaunay triangulation that the complexity is linear in the number of input points. So that means that an n log n algorithm is possible. Okay, two exercises now. Well, the main exercise is to go back to the Voronoi diagram, how we computed this with CGAL, and verify that the duality, if you have a Voronoi diagram, you can take again an example of 10 random points. And actually, the first step in the verification is just to verify that the point set in the Voronoi diagram is the vertex set in the Delaunay triangulation. Then you also must verify that if you start connecting, so you construct this dual graph, that you can here see the coordinates for the list of edges, so you can store them in a list if you like. And as you construct your dual graph, verifying the adjacency of the Voronoi cells, that these are actually the edges that you're going to add. Okay, that serves as an introduction to the software that we are using. To indicate the importance of Delaunay triangulations also for engineering, there is the James Wilkinson Prize for Numerical Software, which was awarded to the software triangle. So numerical software, numerical analysis, this is not really what this course is, but you can see that meshes and Delaunay triangulations are extremely useful to engineering. Excuse me. So this is to indicate the relevance of what we are considering here. This software is also available in Python. So there is the option in this course to go for a computer project. For a final project, you could check out this package and explore applications with this. So this could be a topic for a final project. All right. The Delaunay graph is the dual of a Voronoi diagram. So here is an example of a Voronoi diagram. We have one central site and then 8 nicely surrounding sites. So this leads to an octagon. So I was using this example to indicate that the complexity of one Voronoi cell could be linear. So we have actually 9 points and 8 edges in this central Voronoi cell. And yet the complexity of a Voronoi diagram is also linear. So at the right is the dual of this Voronoi diagram, where we connect adjacent sides with edges. So we add the edges of the octagon, so we have actually a larger octagon in red, and then we have the spikes to the central side, so we obtain a very nice symmetrical figure. It's very nice to look at. We introduced the Delaunay triangulation also as an application for geometric modeling. So triangulations that look nicest actually optimize the smallest angle. So you can also verify if you would start adding other edges, and actually you can't add any more edges without destroying the planarity of the graph. So if you add one more edge, then your graph is no longer planar. So that was also the characterization that we gave last time to any triangulation, which is a planar maximal subdivision. Okay, in words, what is now a dual graph of a Voronoi diagram? Well, the vertices of the graph are the sites, and the edges are the connection between adjacent Voronoi cells. So we're only going to add one edge if the Voronoi cells share an edge. So every vertex corresponds now to a face in the dual. So what are the vertices now of a Voronoi diagram? Well, these are the points that lie at the same distance of three sides. So these are the vertices. The edges lie at the same distance of two sides. So this is just to remind you about what are the vertices of a Voronoi diagram. So with every vertex corresponds a face, and perhaps I should actually try to see if I can go to a two-page. Yes, I can. So here you see the definition in words at the right. One should actually look to the picture to the left. So with every side, we have a vertex. And you see that the vertices, so at the centers of these triangles here, it's not always like that, but the picture is very nicely symmetric. At with every vertex, we have actually, of the Voronoi diagram, we have a face. So this explains the duality. So we have introduced duality also earlier, where lines become points, points become lines. So here vertices correspond to faces and faces correspond to vertices. So it's a different type of duality that we have seen with the arrangements of lines. Now it's important, so you could say that, look, we get a triangulation, so this is a planar graph, but it's actually not obvious from the definition in words, that actually really you get a planar graph. So again, in a planar graph, you have no edges which cross each other. Okay, let's prove this. So, and in some sense, the proof is rather short, so you see on two slides, but it's in some sense not really that self-contained, because it uses the concept of the characterization of the edges. We have characterized the edges of a Voronoi diagram via the largest non-empty circles through two sides. So the edges, they are segments or half lines that lie on the bisector between two sides in the Voronoi diagram. So the bisector is also the diagonal of this largest empty circle, in the sense that it does only contain sides on its boundary. It contains two sides on the boundary. So the center of the circle lies on the edge of the Voronoi diagram. Okay, so this is the important property, that there is no side of that lies in the circle. So any side only occurs on the boundary of these circles. And that is important. So here I drew also the construction for, so let me go through everything again. So this is our running example. So in some sense, the proof is very short if you don't have the pictures. But without the pictures, the sentences are rather harder to read. So you see the circles also shown on the dual graph. Okay, what would this imply now? So suppose that we do have two crossing edges, then what we will see is that the circles would no longer have the property that there are sides in their that there are no sides in their interior. So you can see that if you look at the corresponding circles, that the largest circle then contains a side of the Voronoi diagram, and this cannot be. So the dual graph that is constructed from the Voronoi diagram is planar. Now this doesn't necessarily mean that it is a triangulation. So there is an extra condition that is needed. And here is that condition. So let's first look at the example. Here we have a Voronoi cell, so a face, a face in the dual graph. That is a trapezoidal, that is a trapezium. So it's not a triangle. And this happens when the points are not in general position. When we have degrees in the Voronoi, then we have vertices in the Voronoi diagram that are of a higher degree, higher than 3. So if you look at this vertex here, the vertex has, so in the lines you can kind of see them, the degree of the vertex is 4. 4, by the way, also equals now the um, the number of edges in the dual graph. Okay, in some sense, we should not really worry that much if we are constructing Delaunay triangulations via Voronoi diagrams. We can always very easily add an edge to obtain a triangulation. So for convex sets, triangulating them is rather straightforward. It's not straightforward to then verify. You have many choices. Still, you can pick a vertex and you draw all the diagonals to all the other vertices. So it depends on which vertex you kind of pick or not. So here in this case, there are two different type of triangulations. Because of the symmetry, it doesn't really matter as far as the angles goes, but in some sense it requires a verification that it's indeed easy to triangulate faces that are not triangles in this dual graph. All right, now if the degree of every vertex in the Voronoi diagram is 3, then actually we have triangles. And then our planar subdivision is maximal. And then actually we do have um, a triangulation. It's in some sense not really proven yet that actually we can talk about the Delaunay. Well, we can talk about the triangulation. So we have derived a unique triangulation. The fact that it is an angle optimizing triangulation is actually not yet so clear now. But in the previous lecture, we indicated that was one of the exercises, give an example for which the Delaunay triangulation, that there are multiple optimal angle optimal triangulations. Here we have a criterion. A criterion derived from the Voronoi diagrams. All right. Now let's go back to the original question in some sense. Is the definition well defined? So we say that it is the triangulation. There's this the dual graph, but is it actually the Delaunay? If it's Delaunay with the angle optimum. So here is a slide that we have covered when we talked about Voronoi cells. So we have the largest empty circles. They are empty in the sense that they contain no point in their interior, no site in their interior. So for a vertex, we have 3 points. For edges, we have um, 2 points on the boundary. And the center lies on the bisector, which is typically, the bisector contains also the line segment, the edge in the Voronoi cell, or the half line. Circles, where did we encounter circles before? Well, we had the circle theorem of Thales, and that actually makes the connection kind of intuitively why the Voronoi cells, the circle characterization, actually corresponds to the angle optimal cells, the angle optimal triangulations. Here is a characterization. Um, so if we have three vertices, then there is a unique triangle. So actually, I should have pointed out that um, the dashed lines are the bisectors from the Voronoi diagram, and they are a little bit in the background. What is actually emphasized are the edges in the dual graph. So we see the triangulation here. At the left, we have the vertex characterization. At the right, we have the edge characterization. And you can kind of see that the vertex characterization, so here I drew two of the circles. So for two of these vertices of the Voronoi diagram, but there are actually four of them. So I did not draw the other two. But it's actually those, the left picture is actually the continuation, is continued here. So let's focus on one circle. It circle that characterizes a vertex of a Voronoi diagram. On its boundary we have three sites, three vertices also of the Delaunay triangulation. And then we consider an extra point S here. And with the circle theorem of Thales, we characterized when we should flip an edge or not. The middle triangulation is legal because if we were to exchange the edge PQ for RS, we would actually end up with smaller angles. And I think this can be seen. Whereas with the illegal configuration to the right, we actually should interchange, we should flip the edge PQ with RS. And this actually justifies the definition earlier for the Delaunay triangulation obtained via the dual graph. In some sense, it's only now, and I think the textbook postpones the definition of Delaunay triangulations till very late. So it's only here, and we are in the middle of the three lectures on Delaunay triangulations. It's only here that we can uh, characterize the um, Delaunay triangulation. Actually, that we can define the Delaunay triangulation. So if we construct any triangle, any circle through the vertices of any triangle, it does not contain a point in its interior. And that is explained via these edge flips, which we introduced in the last lecture. All right, we are now obtaining our main theoretical results. So via legal triangulations, so the if we defined the Delaunay triangulation, or we defined an angle optimum triangulation via edge flips. So we would flip edges as long as we can improve the vector of all the angles. That's how we obtained a, an angle optimum, uh, an angle optimal triangulation. So the main result is summarized in the second theorem here, that any angle optimal triangulation is Delaunay, and any Delaunay triangulation is angle optimum. And this is the justification for the concept and the definition of a Delaunay triangulation, which is by now a concept that we have well defined and that we understand quite well. All right, in the third and last part of this lecture, I will outline a randomized incremental algorithm. In the next lecture, we will discuss its cost. Um, It is randomized because we're going to incrementally add points. Um, and there could be unlucky orders, but let's not worry about this. Let's first think about how one would work incrementally. So we have an initialization. So we could actually start from any triangulation. But instead, we we've seen that there is the convex hull construction that is used in scipy. We've seen that last time, and we can compute it also via the edge flips on any existing triangulation. But the purpose of the algorithm that we will outline next is a direct computation. Why is that? Why is there a benefit there? Well, we've seen that the number of triangles is fixed because the vertex set is fixed. So you can actually allocate all your memory right at the beginning of your algorithm. And that's very, very beneficial for the efficiency. All right, here is our initial triangle. We worked earlier with an initial bounding box. So here we think of triangles. So we have the highest bound point. Again, there might be a problem if there are 2 points with the same coordinate. But let's not worry about this. We're thinking about points in general position. Then we pick the leftmost and the rightmost point, or actually here in some sense, if you think about 0, -1, -2, the rightmost point and the leftmost point. So, again, the condition is that any circle that you can make will not contain p minus 1 and p minus 2. So these 2 points must be lie far apart. So that is important. Okay, then you can see what will happen. We will add a point, and here is the addition of the point. So we add a point, and I can now explain this geometrically. We locate, so for any triangle, we have a new point PR. We locate the point inside the triangle. We adding edges um, and adding new triangles. So one has to be a little bit careful um, if we have situations like this when the new point will actually lie on an edge that's already existing there. So we don't have to do, well, we assume that all the points are distinct from each other. We don't have to, so we have to either the new point lies inside in the strict interior of a triangle, or it lies on an edge that is shared between two triangles. In any case, in both cases, we have to replace illegal edges via edge flips. So we have to check whether the edges um, that are of an existing triangle, if they don't become illegal because of that new point. All right, so let's now formulate the algorithm. So we have a subroutine to legalize an edge. So we have a new triangle, um, and we have an edge. So we're going to apply this subroutine to all the edges in a new triangle. So we have to consider the adjacent triangles. So the adjacent triangle shares the edge that we are considering now. Um, so we have to check when we have a new edge so that this is still legal. So we have to every edge, if the edge is illegal, then we will have to replace it. And you see, there are two recursive, so the statements 1, 2, 3, um, they're a little bit cumbersome in words, but if you draw a picture, then actually you can see it, and I will not do it here. Um, I'm surely to do it in the lecture. Uh, but if you make a drawing, then you can see why the steps are fairly straightforward. Okay, uh, there are two recursive calls here because you have replaced, so you have the edge PRPK. You now have to be careful that the edges PIPK, PJPK are actually also legal. Now, this is a recursive algorithm. You may continue replacing and replacing and replacing. So two questions here. Why do we need 4 and 5? And why, so you can have situations where you replaced an edge, but then actually you have to do more replacement. So draw an example where this is needed and make then sure that you will not get into an infinite loop with recursion. All right, we have then the outline of the algorithm. So it's the construction of our um, initial first triangle. So the entire point set has to be inside this triangle. And this might actually ensure that the condition is satisfied, that any circle to 3 points do not contain p minus 1 and p minus 2. Again, this would require some justification. Then some justification is needed as well. Why do we permute the points? Um, and So the main loop consists of this locate step and then the update, using the subroutine on the previous slide to make edges legal. Okay, here is the update. So we have added the point PR. We have located this inside the triangle spanned by the vertices I, J, and K. Now, there are two cases. Either it belongs to the strict interior or the new point belongs to an edge, and an edge which is then shared between two triangles. So we add the new edges and we have to make sure that the edges of the um, triangle that where the new point was in, that these edges are still legal. So you can imagine if the new point lies very close to an edge of this triangle PI, PJ, PK, we actually will have very small angles. So that's a case that justifies the legalization. Okay, the drawing to justify the second step in the algorithm is actually already given. Um, uh, the point is also mm, if we solve the previous exercise, so the legalized edge terminates, but how can you actually be sure that these next steps do not undo the work? Again, verify this with examples and think about the circles. So if you flip, it's because one of the point lies inside a circle. Okay, so we have the two cases. Either it belongs to the interior of a triangle or it lies on an edge. So we have an edge. Um, so we then need to add more triangles. So we have to then for um, for extra calls to the subroutine. Okay, make a drawing to justify the steps in the algorithm. So that is actually my exercise, but I will skip this for now. So this would be an extra exercise to go back to the um, working of the algorithm. Okay, so uh, that concludes the outline of an incremental algorithm for the Delaunay triangulation. At this point, the algorithm, if the exercise of determination is solved, then it is an algorithm. It terminates, and it's also correct if we are always flipping away the illegal edges. In the next lecture, we will cover the costs of this incremental algorithm. Also outline why the randomization is needed. So at this point in time, the algorithm is only outlined. But I hope that this suffices for uh, this first standalone algorithm to compute a Delaunay triangulation, which is unique if the points are in general position. And there is the duality with the Voronoi diagram, in particular the circle characterization of the vertices of the Voronoi diagram. All right, so the exercises are kind of necessary to get through the main concepts in the lecture. The goal of the lectures is that the textbook and the CGAL software becomes more accessible. So the CGAL documentation is quite extensive. So I will come back to this also in the next lecture. Also consider the exercises in the textbook.